компьютер. Так, все отлично. Теперь я вас делаю, все, я записываю. Теперь я вас делаю организатором, и вы будете делиться. Сейчас. Все. Пожалуйста, делитесь, чем хотите.
Так. Окей, спасибо. Сейчас мне нужно найти сюда.
Так, ну пока еще ждем. Народ.
Так, окей.
Володя, а сколько вы доклад будете делать? 2 часа или час?
Скорее всего, 2. Вы хотите...
Нет, ну западные традиции, по-моему, они не такие.
А почему вдруг Володя у нас какой-то человек западной традиции? Он всю жизнь был восточный.
Нет, он же подключился к этому самому какому-то семинару и будет сайт семинаров и будет говорить по-английски.
Да. Сейчас будете по-английски говорить? Ну говорите по-английски. То есть нас смотрят вообще вот отовсюду,
В принципе,
понятно.
Да, в принципе,
Yeah. Can you see my screen?
No.
No. Okay. Nice. But I try to share it.
Okay, something is happening, so maybe try again.
Okay. So I should use this green button at the bottom and then do something, right?
So there is a green button saying share the screen, and then this you push it, and then it suggests several options, and then you choose.
Okay, for me, now I have a blue border on one of my screens, but I assume maybe I should stop sharing video. I don't know.
No, it is unrelated.
Okay.
So video is not related to sharing the screen.
Okay.
Are you using? Oh yes, fine. It is there.
But now I don't know which one. Do you see any PDF file?
No. No, I think it's no.
What about now?
This is your screen of your laptop now.
And nothing on it.
And that's it.
Okay, let me try once again.
Добрый день.
Hello.
Hello.
I managed to somehow minimize my zoom, and now I only have our faces and nothing else, and no buttons.
Oh well, so the moment we see your
okay,
desktop.
I found it once again. I have 3 screens. Maybe that's the problem. Let me try try to close this one, and he can't understand. Okay.
Now we
Does
see
this
the
work?
mm,
Something. You should see something. Right?
handwritten, something handwritten.
Okay. I have
Now,
some.
no. Now it comes the, how it's called, the PDF.
Yeah. So I was thinking about, I have something handwritten and something hand drawn and something like in text.
Yes,
So
that's
maybe
fine.
maybe I should find the reader. Could you read it if it's like this size, or this is too small?
No, it's more or less visible.
This
Yes,
is
it's
visible.
fine.
Okay, nice. How do I make it 2 pages?
Koля Kasowski knows.
Koля, do you know how to show 2 pages at the same time?
I don't know. I use two
Two screens, maybe.
just,
Mhm.
two windows.
Oh, yes,
You can-
but you may open one and the same document in two windows simultaneously and scroll them independently.
Okay, that's a genius solution.
No.
Let me try. I guess that Sumatra will not do it for me, but I will use Chrome or something. Okay. Okay. Nice. So maybe I should start the talk.
Sure.
Can you say me if you want me to start or you want me to wait for somebody?
Well, everybody who is here, I guess, votes for starting.
Okay.
And those that are not cannot vote.
excuse me, is it registered?
Yes, recorded, you mean?
Yes, recorded.
And it is both registered and recorded.
Okay, so at the very end, you will just send us the reference.
Yes,
Great.
as usual. So I apologize because last time I did not record. I forgot to push the recording button for Nina's talk. And therefore, I didn't distribute the link. But I hope if everything goes smooth, today it will be fine.
Okay, let's me start then, I guess. So I will be talking about Bi-Lipschitz embeddings of self-contracted curves into Euclidean spaces. And first, I quickly remind what we mean by Bi-Lipschitz embeddings. So we want to take some kind of metric space, X, and we want to embed it into another space Y in such a way that the distances, the way in which distances changes, they change at most d times in the multiplicative sense, and also they all can scale by some constant c. So this should hold. And the natural question is which spaces allow Bi-Lipschitz embeddings into Euclidean spaces. Maybe you want to do something with your space and it has less structure than you want, and then you want to put it into Euclidean space and use all the structure which Euclidean space provides. So we want to know this. We also want to know this because of like mathematical curiosity, but there are a lot of applications for embeddings. And the first natural condition, maybe, yeah, the first condition which should hold for such spaces which you want to, which can be embedded into Euclidean space, this is the so-called doubling condition. So the following should hold for your metric space X. You should have some number m such that for every point in this space there are other m points which are such that they're so for every point x and for every radius r, there should be a set of points y1, ym such that the bow of radius r with the center in x is covered by some m balls of the half radius, so of the radius r divided by 2. So this is conditioned. It should be pretty clear that that's a necessary condition. So suppose you have something like discrete metric space. So you have all distance equal to 1 and you have a lot of points. You can't hope to embed it into Euclidean space with a small distortion, because since all your points in the potential embedding should be close, you have a bunch of points which are close together, and then by Bi-Lipschitz property they should be separated. So there are a lot of points which are like close together, and they also are separated from each other by some distance. So that's some kind of volume argument will prevent this. But that's not all conditions. But it's, in some sense, this condition is almost sufficient one. So there is this concept of alpha snowflake. So you fix a metric space X and you fix a number alpha between 0 and 1, and you define an alpha snowflake of this space X as the new metric space on the same set of points, which satisfies, for which you define metric by this equality. So you just take every distance into the power of alpha, and magically this will be indeed a distance. And pretty long time ago, Aswad proved that if you take a doubling metric space and you take its snowflake, then this snowflake will indeed admit a Bi-Lipschitz embedding into Euclidean space. And the distortion and dimension of this Euclidean space will only depend on the doubling constant of the original space and on this epsilon, which is showing how much snowflaking do you do to your space. And those spaces are quite interesting. So this whole study of self-contracted curves and the Bi-Lipschitz embeddings is kind of motivated by those curves. So the simplest example it's kind of motivated by curves which are snowflakes. So the simple example is that you take a standard segment between 0 and 1 and take its epsilon snowflake for some epsilon between 0 and 1, and then you get this helix, and it can be embedded into Euclidean space by this theorem of Aswad. But there are some weird stuff happening here. So if you use this Aswad theorem, or there are also some works by also Aswad and Talagrand, which are specifically for embedding such spaces. And for all this works, there is this weird thing that when you take your snowflake and you say that this epsilon goes to 0, so your space it goes to just the standard segment in some sense. So you start from something like this, and then you go to this, and then you go to this. So when you consider such a sequence, your target, either your target dimension or your target distortion will go to infinity. So you have this, you kind of can embed them, but it's very non-uniformly dependent on the space. So maybe I should say it another way. I want to say that our methods for embeddings which we use, they are they deal pretty poorly with the situation when our space is non-uniform. Consider some curve like this and say that something here it works like a snowflake with a big epsilon, and somewhere here it starts being like a snowflake with a small with epsilon almost 1, and maybe there are some segments where it is just 1, so this is just straight line segments. And to embed such a thing, we should use this theorem with different epsilons, and also somehow we should glue it together, and on the parts which are for which it is almost a line segment, we will have like infinite not infinite, but very large dimension. So something weird is going on, and I decided to look at this and figure out, can we combat this non-uniformity of the space which we want to embed, at least in dimension 1. There are also same type of problems if you try to embed some other stuff, which, like, for example, if you try to embed a subset of Hilbert space, there is a big open problem that asks if we can embed a subset of Hilbert space into Euclidean space under assumption that it has doubling. So if you consider this, then you will also see that for some subsets you want to use a SWAT theorem and you will deal with them, but then maybe you have a bunch of subsets where there is almost intrinsic metric and you cannot use a SWAT at all. So there is, once again, this non-uniformity, which is kind of in high dimensions, it's very unclear how to deal with it. But I will try to deal today in dimension 1. So to do this, I want to give this definition of weakly self-contracted curve. So this is a curve. For me, I will. So usually people consider curves which are maps from a subset of real line to some metric space, but here I don't really need this other metric space. I want to just push back this metric from a metric space on our set on the line. So I just say that the weakly self-contracted curve, it will be some subset of the real line with some metric which should satisfy this inequality for some k greater or equal to 0. So if you have some points like x and omega, and there are y and z inside of them, this yz shouldn't be ridiculously long in comparison to x omega. So if you have something like a circle, this is a weakly self-contracted curve with some coefficient, but when the size of this hole goes to 0, this coefficient goes to infinity, and eventually you can't have a closed curve as a weakly self-contracted curve. Also, there is a weird tradition about self-contracted curves. We do not assume that they are continuous or they are given on some kind of, maybe people usually assume that they are given on an interval, but I think I just want some subset of the real line and I do not assume any continuity. And the theorem, which I will hopefully prove today, is the following: that if you have some m, if x some m, then there exists d, which depends only on this m, and there is n, which also depends only on this m, such that every weakly self-contracted curve will be we will be able to embed into Euclidean space of this dimension n with distortion d. So as soon as we control the doubling dimension, we always can embed the self-contracted curve into some Euclidean space with controlled dimension and with controlled distortion of embedding. So this is like an ending of the first part. Maybe somebody can ask some questions, because or maybe somebody can do some remarks. I want to change my cursor. I made a beautiful cursor.
I have a question, Volodya.
Yeah, sure.
Why you call it weakly self-contracted?
Yeah.
What is not weakly?
No. Why?
Why it is weakly?
So there is another concept, which is just a self-contracted curve. So do you want me to talk about it a little bit? So in this concept, we ask that x omega should be greater or equal to xy. So if there are 3 points, say x, y, and omega, then the distance from x to omega should be greater or equal to the distance from x to y. And this weakly self-contracted property is just the consequence of the self-contracting property and the triangle inequality. And also, we will see that if you take a self-contracted curve and you do a Bi-Lipschitz, apply some Bi-Lipschitz map to it, then it should be obviously that it transforms to the weakly self-constructing curve, and every weakly self-constructed curve contracting curve can be obtained in such a way. So this is just a Bi-Lipschitz version of the notion of self-contracted curve. So let me.
So doesn't the dimension depend on this k, the self-contracting constant?
Okay, nice question. Yes, I guess I should write that they all also depend on k. Yes, that's correct. We will pretty soon we will get rid of this k, but it will be. So I guess the dimension does not depend, but the distortion will depend. Yeah. So that's the right way to say. So dimension only depends on m, and distortion will depend on k. So I have this. So now I have this cursor. I was so glad to do it, and now I have to use it. So now I lose your time to change my cursors. What a shame. Okay, maybe now you will see better where I'm trying to show something. So let me just quickly deal with this k. So the second part is, I call it domestication of theorem 1, of theorem 2 for some reason. Okay, I don't know anything. So yeah, here I just formulated the strongest statement I could formulate, and now I will reformulate it to the statement which is easiest to prove. So now I want to new definition. I want to call I want to take a subset of a real line, and once again to take some metric on it, and I want to say that this metric is monotone by inclusion if this inequality holds. So the same inequality, but with the constant one. So I have somewhere a beautiful monotone by the inclusion curve, and this is already not monotone by inclusion. So this is the new concept. And let me go here. And now I want to show that if you have a weakly self-contracted curve, you can very fast transition to the curve monotone by inclusion. So you take some weakly self-contracted curve and you change your metric by saying that, so suppose you had some points x and omega, and you define the new distance between x and omega as a supremum of distances between points which lie inside the segment. Pretty straightforward definition. It should be, some stuff should be clear about the thing. Maybe it is clear that it is k equivalent to the original. So this change of metric is a Bi-Lipschitz map. But maybe it's less clear that it is indeed a metric, but it also should be obvious. So suppose that you have 3 points A, B, and C, and you want to see that there is a triangle inequality. So just the way this metric is defined, we have that AC is greater than other two. So the only problem with triangle inequality, which should be afraid of, is that AC is greater than AB plus BC. So let's write what AB is. So no, there should be AC. So we say that AC, so this distance, it is so it is the maximum over all UV inside it, and we can take some UV such that they are equal to AC up to this epsilon. And then we say that this UV, it can be dominated from above by the sum of UB and BV, and the distance, the new distance between BC is greater than the old distance between BV, and the new distance between A and B is greater than the old distance between U and B. So we have that this original distance between A and C is less than the, not the original, the new distance between A and B is less than the new distance between A and B, and the new distance between B and C up to some epsilon. And this epsilon is arbitrary. It can, we can say it to go to 0 and everything will be fine. So this is just by this Bi-Lipschitz move, we got rid of this k forever. So I didn't even knew if my stuff depends on k or not, because I forgot about it. It's gone so soon. Okay, I wanted to talk about some other properties.
But now the doubling constant could change too, right?
Yes, yes, that's the next remark. The doubling constant, when you do a Bi-Lipschitz map to your space, your doubling constant can change, but it changes in a controlled way. So the new constant depends on old constant and this k.
So the final parameters, dimension and distortions, depend on actually on
Okay,
on the
you got me.
k and doubling constant, right?
Yeah, maybe right.
Or some exponential or something like that.
Yeah, maybe the resulting dimension also will depend on this constant k, because since it got into the doubling constant, into our doubling constant, probably our dimension will depend on this doubling constant, and thus both dimension and distortion will depend on this constant k.
And another question: this strictly monotone by inclusion, is this just an equivalent to self-contracting?
I think not. So self-contracting, it's usually self-contracted is assumed only in one direction. So if you go from, I don't know, so you have that for A, B, and C, you have that AC is greater than AB, but not the other way. So AC shouldn't necessarily be greater than BC. And I assume that for some gradient curves, which are the source for self-contracted curves, that will be indeed only in one way. But you can do it in both ways by this Bi-Lipschitz move. Okay. So let me try to go next with this theorem 3. The theorem 3 is just the previous theorem, but hopefully with less amount of mistakes. And it is, maybe not, maybe I shouldn't go with theorem 3. Maybe I should talk a little bit how to improve this curve a little bit more. So at this point, how can I move this? This is annoying. Okay, so we got our curve to be monotone, but I want it to be strictly monotone, and I also want it to be on the segment, I guess. So suppose that I have some kind of monotone curve. Then I can approximate it with finite curves. So I just take some finite amount of points in this curve, and they will have the same doubling condition. So the same doubling condition will be holding for this subcurve. And if I embed every such finite subcurve, I can then embed the whole original curve by using some kind of diagonal argument. So I will embed the nets which are thinner and thinner, and take some kind of limit. So yeah, I don't really want to go too deep in this argument, but to embed, this is the general statement for every metric space, which is, I guess, okay, maybe it's separable metric space. So if you have a separable metric space and you can embed every its finite subset into Euclidean space, and you control the dimension and distortion, then you can embed the whole space with the same dimension and distortion. So to deal with those monotone curves, we only have to deal with monotone curves which are supported on finite amount of points. And if you have a finite amount of points, we can make our curve strictly monotone by just adding a little bit of the standard metric of the line. So you can take an epsilon which is so small that when you add it, it will be like 2 Lipschitz map. So you will transition from the curve which is just monotone to a strictly monotone curve. So this inequality will be a strict inequality. And final improvement for our curve, I want to make it continuous once again. I want to have a continuous strictly monotone curve. Once again, I want to avoid explaining this in full detail, but you want to somehow glue segments between those points. So you have a finite amount of points, and you take every 2 consecutive points, and you glue a segment between them. But then you have to define a metric between every 2 points. So you have a point here, and you have a point here. How to define a metric? We want to do it in the way that this curve is still strictly monotone, and the way to do it is to say that the intermediate point, suppose you have some segment and you have an intermediate point which divides it in like lambda and 1 minus lambda, then you say that this intermediate point, you will see it as a measure which is supported on those 2 points, and it has weights 1 minus lambda and lambda. So you convert this point to a measure, and then you can use Wasserstein 1 space. Then every such segment will be isometric to the segment of a real line, and this whole curve will be strictly self-contracted, and it will have the doubling constant, which is controlled by original doubling constant only. So in this way, we transferred our super ugly curve into a nice curve, which is on the segment and strictly monotone. So new theorem is, so the simple version of the theorem says that if you fix m, which is a natural number, and then there is a distortion, so there is a d which depends only on m, and there is this dimension which also depends only on m, such that for every segment and a metric on it such that it satisfies those three properties. So the first property is that it's strictly monotone, the second that it has doubling with the constant m, and the final one is that it is continuous with respect to standard topology. So yeah, then this gamma allows a Bi-Lipschitz embedding with the constant d into Euclidean space. So this is kind of simple to deal with. It's simple to deal with this theorem than with the original. Okay, I can take some questions if you have. I have a natural break. Does anybody have any questions? Is everybody already asleep? Okay. Maybe I should open chat. Nothing goes on in chat. Okay, so let me go further. So now I got this curve, which is, there are a bunch of different properties of this curve, but it still looks like there is no immediate structure on this curve, and we want to do embedding, so we want to go and create some structure on it. So I will do the following. First, I will fix this number alpha, which will be clear later what it means. And there will exist this number mu, which will depend only on m and alpha, such that we can decompose our curve in the following way. So we can start with, so suppose that's the starting segment on which is our curve, and we will find, so the proposition claims that if you fix bunch of constants, then you will find numbers L2, L cent, R cent, and R2, which are all not consecutive. So the sequence is monotone, such that three segments will be equal. So this guy will be equal to this guy and to this guy, and they all will be equal to the 1/3 of the original segment. So what I've done, I found two holes or clusters of, so I found those parts, which if I remove them, the remaining part looks pretty much like the original in terms of total length, I guess. Not length, but distance between ends. So I would try to take those guys and kind of move all the stuff which happens here to some kind of other dimension, and since and with those parts I will try to stay in this in the same dimension. Maybe that's not clear. I should talk about just finding stuff. So at this point, I said that the first part of the claim that we can find this decomposition into like 5 parts, and these 3 are equal and equal 1/3 of this. But there is an additional requirement that for those red parts, there should also hold one of the following 3 properties. I guess at least one, but okay, it's probably only one can hold of them. So one situation which will satisfy us, that's if those 2 points are somehow good together and those 2 points are good together. So we started with our interval, we moved to 1/3 of its length from the left point and for 1/3 of its length from the right point, and we just get that the distance between those 2 is again 1/3 of the total length. Then we are fine. And maybe that's not happened. Maybe something sits inside. Then the other situation which we are fine with is that if those 2 guys are equal to each other, and they also are smaller than the diameter of, so the original distance between ends multiplied by this alpha. So our construction was started from, our proposition started from us fixing alpha, and alpha controls how small these holes can be, those holes can be. And the final third option, which we allow to happen here, is that each of those segments can be decomposed in a set of holes. So there exist some additional numbers, L3 and L4 and Lm, such that and the same in the right hole, such that the corresponding segments are equal to each other, and they are trapped between alpha divided by 3 multiplied by the diameter and the thing divided by 2. So in the second case, we just asked those holes to be small, but if we have a bunch of holes, we ask them to also be at least so we ask them to be big too. Okay, this is the formulation. There is also some terminology, so I will later say that for this hole, this segment L1 R1 is a parent segment, or maybe I will say that for a segment L1 L2, this segment L1 R1 is a parent segment. So if at some point in time I removed, I got this structure with holes on my segment, then I automatically will think that everything what I've got has this segment as a parent. And I can sketch the proof of this theorem. Is pretty easy actually. So when we take those points L2 and R2, we have no freedom. We just should take 1/3. So the freedom of construction starts when we try to find those other points, and it's some kind of continuity argument. So you take 1 point on L2 and 1 point on R2, and you say them to go closer together, but in the way that the distance from this point which goes to the right from it to L2 is the same as the distance from the point which goes to the left and to R2. So you grow those segments, and at some point either you will find that the segment inside them became equal to 1/3 of the original segment, and then you say, hooray, we found this case 2. Or maybe your segments which you grow here become too big. They become greater than alpha divided by 3. Then you say, okay, we stop them, and we add our first points like L3 and R3. So suppose that we grow those segments here and here, and they became equal to something, I guess, alpha divided by 6 multiplied by diameter. They're equal to this guy. Then we stop them, and we continue this growing from L3 to the center, and from R3 to the center. So we will get a bunch of those segments, and at some point we finally will get that our center segment is equal to 1/3 of the original, and then we should do something to make our segments. So we want this inequality for every pair of segments. So we will go back one step, and we will redo our procedure, and it can be seen that indeed we will be able to make all segments pairwise equal, I guess. So I talked a little bit how to do this. That's a continuity argument, not much more here. If you start to do this, you will probably find the way pretty fast. And so yeah, this is the way how we find some amount of structure on this segment. We found some holes in it, and we also found some more segments. And now in the fourth part, maybe we have some questions before the fourth part. Maybe not. I actually lost the window which show faces, so I can't see if you are asleep or not. Don't know how to get it back. So I will talk a little bit about this first part. Okay, somebody wants to say something? No? Okay, so now we can construct the embedding. So first we want to construct something like a counter set by repeatedly doing this procedure of finding holes. So let me find this part. I want to define this set K. I will do it inductively. So I start from gamma, which is my metric space on a segment. And on the first step, I just find those holes as in the previous part. And I remove those holes from my segment. So I get this set K1, which just the original segment without those holes. But it still has those points which are between holes. So holes are assumed to be open. And then on the next step, I do the same to the remaining segments. So from one segment, I got 3, and I do this once again. So I do this repetitively, and I get some kind of counter set, but I also have these additional points which sit between holes. So I define this resulting set K as the intersection of all Ki, which I construct in this way. And I will call the holes, those holes I will call the holes of the first level, those will be holes of the second level, and so on. So everybody will be living on its level. And now I want to say what is the right covering of holes. I want to cover holes in such a way that the first requirement to be right is that if they are in the same cluster, so if they were obtained on some step, if they have the same parent, or in other words, at some step they were obtained in this way from the same parent, then they should be, if they sit in the same cluster. So when we obtain a bunch of holes from the same segment, they come into clusters left and right, and if they sit in the same cluster, then they cannot have the same color. But if they sit in the different clusters, then they can, and they actually have to have the same color if they are symmetric to each other. So this coloring should look like this. And even here I draw some small guys, and this guy is the same color as this one. So yeah, it should be symmetric, and also it should be such that the guys in the same cluster are of different color. And now I can define the map, which is the address map. So it takes a point in my set K, and for a point T in my counter set K, I define AT as its address in the base tree. So I guess every point in the standard counter set has this type of address. But here we also have points which manage to get between holes, and for them I will probably move them all to the right and say, okay, if you got between holes, you can get like next number on this step, but then you will have zeros on all further numbers in your address. So this defines the address for each point in our counter set K. And the next step I want to define, so this will correspond to one dimension in our target Euclidean space, but I want to to have a dimension for each color. So I take I enumerate my colors with the numbers from 2 to mu, because the first number is already corresponds to this to the address, so they will be numbered from 2 to mu. And okay, maybe I should talk a little bit about this mu. So I say that there is a right coloring of my holes into mu minus 1 colors. So this should follow directly from the statement that when we construct those holes, we can't get too many of them. I forgot to talk about this. Let's return to it maybe. So yeah, so there was this constant mu which controlled how many of these holes we could get. So we could get mu minus 2 holes or something like this. And the reason why we can't get too many holes here is that for every 2 points, which are ends of some holes, so maybe. If 2 points are ends of some maybe distant holes, they are at least separated by the length of some hole and the length of all holes which are. If we have more than one hole in the cluster, then the size of the hole is bounded from below by this number. So it's bounded by some constant multiplied by diameter. And then if you have too many of those guys, they will give you an alpha divided by 6 multiplied by diameter separated set. So they all also will sit in a ball of the radius diameter of G around, say, like left point. So you have an upper bound on the amount of those segments from the doubling condition. So we control the amount of points, and hence we control the amount of colors. And now I have to return. I'm a little bit lost. Where am I? So yeah, I'm here. For each point, for each color, we want to give it a dimension. So we define those functions h, which map from our contour set to the real line by this formula, which is questionable. We say that, say, we have a point here, and we want, or maybe here, we want to give it a number corresponding to the green color. So we look for all segments which are to the left from it, and every segment which has, for every segment we will add to our sum, but also there is some problem with brackets here. So but for the, if the whole were in the left cluster, it gets the plus sign, and if it were in the right cluster, it gets minus sign. And we sum all those guys, and we get the value of h in the point T. So we sum up all the holes which are to the left from us, and we give them the sign depending on were they a left or a right hole when we cut them from their parent. Maybe this definition is not correct, because their total length will be, at least this sum, it does not converge absolutely if you have some kind of snowflake, but you can say that that for every level you can, if you look, take some point and look to the left from it, for every level you have at most one non-compensated hole. So so let's say we look at this level, those two holes, so I want to see green holes, and those two are compensated, so we have 0 impacts from them, and this one is uncompensated, so we will get it with the plus sign. So the correct way to write this formula is probably this one, which says that we sum first for all levels. So our first parameter is level, and if on this level we have an even amount of holes of this level to the left from us, we take 0, and if we have an odd amount, we take the one which is the closest to us, and it is the only one which is uncompensated. So we also can see from here that h is non-negative, but it doesn't matter at all. So now I define those holes, those functions hk, and the next step is to define our embedding on the set k, on the contour set. So I start from taking the ends in such a way that I embed the ends isometrically, and I also ask them to be allocated in such a way that they only are different in the first coordinate. They only are distinct in the first coordinate, and all other coordinates are the same. And then I define the map phi on K by this formula. So I take the original point, and I take the vector from the start to end, and I multiply this by function xt, which is just a value of address. So we define here the address of point t, and this address can be interpreted as a real number. So we take this real number, which corresponds to address, and we multiplied it by this vector from the begin to end. And that's the formula for the first coordinate. And the second, the other coordinates, they are just those values of functions hk. So this is it. We embedded our curve on the contour set. And to embed it in other places, we do this stuff repeatedly. So when we define our curve in this way, there are several good things happening to us. The first one is that for every hole, the map is isometric on its ends, because what happens on the hole is that just one hk changes, which actually corresponds to this hole's color, and it changed exactly by the length of this hole. So this is an isometric map. It will be also an isometric map on segments. I don't know why it could matter. I assume that doesn't matter too much, but it will be. And since we have this isometric map on the ends of holes, we will just do the stuff repeatedly. So next, for every hole in our contour set K of G, we will consider a curve which is our curve supported, the part of our curve supported on H. And we can define this embedding is in the same way. The only difference will be that here we had our first coordinate was our main coordinate, and here it will be the coordinate which corresponded to its color. So we will get the similarly embedded curve for each of those holes. For each of those holes, we have a contour set which is produced by this hole, and on each of those contour sets, we can define our embedding phi. And then we can glue this all stuff together and get our hole to be defined on your original contour set, and also on all those contour sets which corresponds to holes in it. And then we do it for every hole of every hole H. So we do the stuff repeatedly, and eventually we define our curve on some set which is dense in the original segment, because we on each step we cut our segment in segment of smaller. They are at least 1/3 of this original segment. So the union, after we're done doing all those steps, the union will be dense. And if we show that it is Bi-Lipschitz map on this set, then we can just extend this map by continuity, and we will get the Bi-Lipschitz map on the whole thing, or on the whole segment gamma, I guess. So this is it about construction. Maybe you have questions. Probably we should discuss construction before I will go to the proof or something.
Okay.
I can't hear you.
Yes, I mean, yes, let us discuss construction first.
Yeah, let's discuss construction. So, is it confusing? Do you believe me that we are done with? So that I defined the curve, that I defined the map, or it's not defined. I don't know.
Okay, well, somebody else is asking.
Okay. Okay.
Maybe the question.
Okay.
Well, what it's difficult to subdivide given segment into 3 equal subsegments without further condition you put it in proposition 8. Simply divide segment into 3 equal segments as in proposition 8 without following properties.
So this step should be, okay, let me think about it. So to get just the decomposition which will satisfy this one, but those ones that should be pretty easy. Yeah, first you take there is only one way to define L2. That's the point which has the distance 1/3 of thing. And then you say, okay, by continuity, you just take two bugs and say them to go together to the center, but in the way such that for each bug, its distance to its starting point is the same that for another bug. Or you maybe even don't need it at this point. Maybe you just, okay, to get this just first property, you just say them to go together to meet each other, and at some point by continuity you will get that the distance between them is 1/3.
Okay, thank you.
Maybe anything else?
Are you going to make a break?
For sure. Let's do a break. Let's do a break now.
Okay, great.
Because
For how long? 5 minutes?
I guess for 10 minutes. I
10
guess.
minutes. Okay.
So I am back. Don't know about you. Should we continue?
Yeah, I think yes.
Well,
Okay, let's go. So, okay, I think that we can go with proving something. I don't know if the construction is clear, but let's go to prove something. I would prefer to talk about construction more if it's unclear, but since you are not talking what's unclear, so I will go to the proof then. So the first claim is of the proof is that our function is Lipschitz, at least on K. So the first statement is that the phi1, which is the first coordinate of the embedding, is Lipschitz. And then it's 9 Lipschitz, and the other coordinates are 5-tooth Lipschitz, or how to say, 5-half Lipschitz. I don't know how to say stuff in English.
5/2.
5/2. Not sure. Okay, so why is Lipschitz? So let's start from the first one. So the first coordinate, it worked as follows. So you took a number, you took its address, and then you multiplied the, so from this address you got a real number, and you multiplied it by the vector from the starting first point of our segment to the last point of our segment, and yeah, that was how the first coordinate was constructed. So suppose that for those 2 points you have that they're Euclidean numbers, Euclidean, no, how to say it, real numbers which correspond to their addresses. They are locked somewhere between 1/3 into the power of k and 1/3 into the k minus 1. And how this can happen? This can happen. So to this to happen, there should be some number m. I don't know where is my cursor. So there should be some number m which is greater than k, such that those two addresses do not coincide at this m point. And the first case is when they are different by 2. In this case, so we had this u and it gone. I assume that u is smaller than v, so at step m it gone to the first segment, and v gone to the last segment, so they are separated by at least this segment in the center. So it went in 1/3 into the power m of m. So we have that the distance between v and u is greater or equal than this guy. And we have that m is smaller than k. So we have this. And this means that, this is the distance between the images of u and b. So one of those guys is v. I don't know which one. Yeah, this is the distance between images of v1 of u and v. We got d because we multiply by the vector from the original point to the last point of the segment, and this is our uv. And for this guy we have this inequality, so it was what it was less than this guy, and for this we have this inequality, so we substitute them and we get that this is indeed less than 3. And the second case is that they got, so this number m on which they are distinct, it happened, but they only have one difference of 1. So then there should happen a number j which is greater than m, but less or equal, but great, it is greater than m, but greater or equal to k plus 1. and this number should satisfy. So it is the first number such that Vj is not equal to 2 and Uj is not equal. Vj is not equal to 0 and Uj is not equal to 2. So what happened here that Uj go to the left at some point and Vj go to the right. That was the m step, not case, and then they could go closer together on each step, so they can go in the closest segment to each other. But at some point this should stop, because otherwise they will get too close together and we will not have this inequality. So they should stop going to the closest segments at some point. So this happens on the step J, and those in my picture V gone one segment to the right, and thus on this step we see that the distance between U and V is at least this segment, which has the length of 1/3 to the power of j. So we have this inequality for them. Once again, we substitute this into this formula and we get that it is less or equal to 9. So we have that V1 is Lipschitz. Now I should say about V2 of Vk, if nobody has any questions. So why the other guys are Lipschitz, or in other words, why H is Lipschitz? So suppose you fix 2 points, U and V, on in our K. Then what can be said about holes which are between them? So we take the biggest hole between them and we just majorize it by the length of UV. So UV are both in our contour set, so they can't cut the hole into half. So if the hole is inside, if the hole of color I is inside, then it is completely inside of the segment. So we took the biggest of such holes in terms of level, I guess, not in terms of length. So we took the hole which has the smallest level, and we say, okay, we just majorize this length by the length between U and V. So this is this part. And for the holes which are of smaller level, we know that with each of such hole, we will contain also a segment which has the same parent. So when you go from the some hole H of color I to the hole of the same color which has level greater or equal to the level of H, you will always cover, but by your path, some of those segments. So if I had some hole which was here and I was going to this green part, I will always cover this segment, which is the segment with the same father, with the same parent as this hole. And this number alpha, it was we asked that each hole is less or equal to 1/6, less or equal to 1/3 of the diameter of, less or equal to alpha divided by 1/3 of diameter of gamma. This means that this segment will be always greater. So this hole will be less or equal to alpha multiplied by this segment. So if alpha is small, we always have that this segment is much bigger than the hole. So returning to here. So we take the biggest of such segments. Its length is, say, I. We know that from each level we get at most one uncompensated hole, and its level, and the first of them will be alpha times smaller than I. So the second of them will be 3 times smaller. So how to say it? It will be majorized by the segment of the which is 3 times smaller. So we will have this bound. Also, yeah, I'm not sure about this inequality. So we want to estimate it from above. We want to say that this is small, yeah, and we say that it's just h. Then we estimate the first of those holes like this. Okay, yeah, that's right. So for each hole, we estimate here by the size of the segment, which has the common parent with it, and we get this geometric progression. We sum it, we get 3 divided by 2, and in result we get this number, 5/2 of an h. So this is about Lipschitz property on K. And the next part will be, we will be taken okay, let's start from the lemma, I guess. So there is this proposition which is actually a lemma. So I want to consider the following picture. Suppose that this is our started segment and we took some point t, and we take theta 0 will be just the first point of our segment. The theta 1 will be the point in the, so our t could go into hole of the of our first contour set. So if this happened, we say that theta 1 is the first, the left point of this hole, leftist point of this hole, and theta 2 is the leftist point of the next hole in which t happened to fall when in the contour set, which was on this segment, and so on. So we look like t falls into holes, and for each of these each of those holes we take the leftist point, and we get the sequence of theta. And I claim that if we sum all the segments, so we skip the first one, but we sum this one and this one and this one and so on, we will get not that much in comparison to the distance from the theta 0 to t. So if we think that this alpha is small, this alpha controls how small the hole is in comparison to its parent segment or its like brother segment. So we usually think that it is small. Then this inequality says that the sum is small, and why it is. So for each the sum we can measure it from above. So this is not equality. This should be inequality. This guy is greater or equal to this. So for each segment, we say that okay, this segment is a part of the whole, and the previous guy contains the segment which is a brother to our whole. So if this was the first whole, then this guy was 1/3 of this, and this whole was just alpha divided by 3 of this or less. So we can say that this guy is less or equal than this guy multiplied by alpha. So we shift all of our segments to the left and get this alpha. And we do this stuff further. So if you have some segment here, you can shift it once again and get one more alpha. In result, we get this, that we get this segment and bunch of alphas. And if we assume that alpha is less or equal than 1/2, this is less or equal than 2. So we got this inequality under the assumption that alpha is less than 1/2, which actually I assumed indeed. And now we will apply this proposition to prove a bunch of statements about how our function phi changes from the value in the beginning of the segment to some intrinsic point. So once again, theta 0 means the first point of our segment gamma, and t is some point inside. And the first claim that if alpha is pretty small, alpha is less than 100, then phi, so the change of phi between those points is pretty big. It is one-tenth of the distance between them. The second claim is that actually, so this was the coordinates corresponding to x, so uncovered coordinate, and it was big. And for all coordinates which correspond to covers, they are small. They are at most 18 multiplied by alpha, which we think is a small number, multiplied by the distance from the starting point to our point. And finally, we just estimate the, I don't know what's written here. It's probably not true. I wanted to write that just function phi. So the whole function phi, it is Lipschitz if you consider those 2 points t and t0. So here should be phi theta 0 minus phi theta less or equal than theta 0 multiplied by t. Let's try to prove it. So there should be actually something said about the first property. So this picture is about it. So I want to take a point t prime as an end of a segment which starts at theta 0 and it's right, and so it will be the biggest segment which starts at theta 0, but its right end is to the left from t. So I suppose that I start with our original set gamma. I found this first cluster of holes, and so I found my first 2 clusters of holes, and I got those 3 segments: the first one, the second one, and the third one. And at this point, I know that my original segment was its right end was to the right to t, and this segment that I got on this first step, its right end was again to the right to the t. But if I divide this segment once again, I get this point. So here I finally got a point which is the segment and which is to the left from t. So this is t prime. And for this point, if I consider phi prime minus phi theta 0, so here I should write phi1. So I look at the first coordinate, the coordinate which corresponds to x. And this is just so this says that this guy is greater or equal than 1/3 of this guy. So we got this t prime was the first to the right. So we have that this segment gives to the first coordinate and at least 1/3 of what this segment gives, exactly 1/3 of what this segment gives. And then we say that theta 0, theta 2 primes is greater or equal to theta 0 t. And finally we say that phi1 of theta 1 is greater or equal than t prime. So the value of the first coordinate at t theta 1, which is the hole in which t fold, it should be to the right from t prime, because yeah, everything to the left, everything to the right from theta 1, which is to the left from t in this hole. So this t only can be to the left. So we get this, and this means that if you indeed write here phi1 and here phi1, you will get that that the value of function phi phi1, so the difference between the value in this point and in this point is at least 1/3 of the distance between this point and this point. And then we wanted to get this kind of thing, but we will lose it while transition from theta 1 to theta 2 to theta 3 and so on. But we actually will not lose it because we had this theorem which said that all those guys are very small, so their sum is actually small. And we already had that if we lie in the same Cantor set, so each of those points they sit in the Cantor set, so we have a Lipschitz property with constant like 9. So in this way we get the first property, and to get the second property we just apply the previous lemma. So we knew that we know that on the first step, on the step from theta 0 to, so we want to say that phi I doesn't change too much when we go from theta 0 to t. So on the first step it doesn't change at all, because this step corresponds to does not correspond to a color, and everything else is small, so you get this inequality. And to get the inequality for phi in general, you just say that you just say that on the first step when we transition from theta 0 to theta 1, only the first coordinate changes, and it has Bi-Lipschitz distortion of 9, and then you for the remaining parts only one coordinate which will change on each step, and it will be also dominated from above by 9 or something like this. So you will get this one, this inequality. So I guess I don't have picture for it. That's a shame. So I wanted to show a Lipschitz property for phi now, but I don't have a picture for it. I forgot about it. Maybe I can use some other picture. So let's use this picture, for example. We have that we can assume that if we take some points u and v, and we want to show a Lipschitz property. Let's use this picture. So this is u, this is v, and they both, we can assume that they fall in different holes, or at least one of them didn't fall into a hole, because if they both fall in the same hole, we can just transition to this hole and prove this Lipschitz property for the curve which has support on this hole. Okay, if on the first step we should probably just take those points, and for all the steps where they fall in the same hole, we just transition to the curves which are supported on those holes. And finally, we get to the curve on which they do not go into the same hole. So U is somewhere here. Maybe it is in a hole, but not in the same as V. And we know that we have the Lipschitz property on this interval because it is not an interval between, it is interval between 2 points which lie in our Cantor set. And for this segment, we have a Lipschitz property from here. This is it. And here we also have this Lipschitz property. So in result, we have like, and each of those lengths is bounded by the length between U and V by strictly monotonicity. So we will have 27 plus 27 plus 9, sum up those Lipschitz constant and get the Lipschitz constant for phi. So that's Lipschitz property. And to show Lipschitz property, I once again need the lemma. Let me try to find the picture for it. So yeah, here's the picture. So the story here is the following. We took some hole, and then we took an interval which starts, I don't know. So this interval starts in this hole, and it is not very long. So the formal, let's try with this formal statement because I can't proceed here. So suppose that we took some points U and V, and suppose that H is an intersection of some hole with the segment UV. And we say that for every C, such that the distance from U to V is small in comparison to the size of hole, so it's not very small. So this alpha is we take its very small number. So if C is not super small, then UV can be bigger than H, but it is not. It is controllably big in terms of H. And if this inequality holds, then we have two statements. The first one is that if some hole of the same color intersects of the same color as H intersects this interval UV, then the length of its intersection with UV can be bounded from above in this way. So it's bounded by H multiplied by C. And the second thing is that if you happen to be in our Cantor set, so it does not fall in any holes, and we denote by V prime the left end of this hole, then we can control the change of coordinate corresponding to the color of H. So we say that the change of coordinate of this coordinate between U and V prime is less or equal than H multiplied by something which we can by C and some parameter. So here we think that alpha is very, very small. Then we can take a reasonably small C, and then we will get that. So we will get that this function changes not that much in comparison to how much it changes on the interval V prime V, where it changed by H. And here it will be like 5 halves multiplied by 1 divided by 100. So it will be small. So how to prove this? To prove this, okay, starting with the first part. So we claim that if our segment intersected some hole, then this intersection will be small, and this should be kind intuitively clear because we had when we cutted our holes and they were they have those segments with the same parent, so they have those brother segments which were close to them, and those segments prohibited any reasonably big hole from being here. So how to say that's formal? Suppose that we just define this intersection by t, and we suppose that this inequality does not hold. So this t has a length of at least c multiplied by h. That means that then we take the one from t and h which has the smaller level, and no, we take the one which has the higher level. So it has the higher level, and it has a length at least of c multiplied by h. Then we know that its brother segment which separates them from all of the whole of the same color with a greater level, this brother segment will be of a length at least this one. It will be their length divided by alpha. So it will be this one. And thus we have that the distance between u and v, or between the right end of t and v prime. So the distance between the right end of t and the left end of h is at least this number, which contradicts with the statement that uv was less than this number. So this cannot happen at all. And to prove the second part, where we claim that the function corresponded to the color will not change much, we say that first of all, let's deal with the so how exactly this function could change. It changes only because there are some holes between u and v prime of the color of the same color of its color, which is the color of h. And for those holes, we have, by the first property, we have that they are small. They are at most c multiplied by h. So at least biggest of those holes we can just majorize by c multiplied by h. And then for all other holes, we have that when we get them, we also get an brother segment to them into the interval uv with them. So we will get that all the smaller holes of the same color, we can majorize them by the length of this segment multiplied by alpha, because each hole is less than alpha multiplied by its segment. And then since they all correspond to the smaller and smaller levels, since they all have smaller and smaller levels, we will have this geometric progression, and we sum it, and we say that since this E was a subset of UV, we can substitute E by UV, and UV was majorized by this property from above by H and C and alpha, and in the end we get this guy. So we get that on interval which are not much larger than our hole, the change in the coordinate corresponding to the color of this hole is pretty small in comparison to the change which occurs on this hole. So this is the lemma. And finally, we can prove Bi-Lipschitz property. I have, I guess, 8 minutes to do so. To prove Bi-Lipschitz property, we consider a bunch of cases. I'm lost. What's going on? What is this 7-1? Okay, I already talked it here. Okay, that's what's here. I'm confusing myself. So yeah, final statement is that if alpha is less than 100, then phi will be Bi-Lipschitz on those. G prime was, okay, maybe I forgot to talk what G prime is, but that's almost all gamma. So we added a bunch of stuff, but we did not do, this is the dense subset in gamma, which we got by taking our first Cantor set, then adding all Cantor sets for the holes in it, then adding all Cantor sets for the holes in the holes of the original Cantor set, and so on. So if we prove that if alpha is small, then phi is Bi-Lipschitz on gamma prime, then it automatically Bi-Lipschitz with the same coefficient on gamma. And we claim that that's indeed true, and the constant is not. So above we have like absolute constants everywhere, and at some point it should end, because probably there are some curves which are ugly enough to not allow always like constant distortion. Some curves which are, I guess, very snowflaked, has a giant doubling constant. They will not allow any, they cannot be embedded into Euclidean space with small distortion, I guess. Maybe not. Okay, I confused myself, but at least I get this constant which depends on mu, which was the amount of holes which live in one cluster, and the upper bound on amount of holes which live in one cluster. So we will parse some cases, and first we fix U and V, for which we want to prove Bi-Lipschitz, and we assume that they are, once again, we assume that they not lie in the same hole, and we take the biggest thing which happens into interval between U and V, and by biggest thing I mean either segment or part of the hole cutted by this segment, or just a hole. So there should be hole here, but so I took some segment, I took UV, and there are segments on it, and there are holes, and there are parts of holes. This hole started here, but it never happened to end because we finished our segment UV. So every of those guys compete between each other to get the biggest in terms of diameter, and who wants, we will deal with him. In the first case, the segment wants. So there is a segment which is greater, which is bigger than all other things, and I claim then that then this segment, its length is at least 1 divided by 10 of the length of UV. So the distance between ends is at least 1 divided by 10 of the distance between ends of U and V. Why is that? So suppose, actually I probably messed up this constant and have to take 1 divided by 20 here or something. So suppose that you have this E and it is really small, it is less than 1/20 of UV, then you know that it probably lives in some parent segment, and you know that UV goes into one of the side at least 10 times longer than E. So you can take UV, go 10 times this distance to the right, and you will still be in the UV. Or you can either this, or you can go this way to the left, and in this way you either will get the segment which is parent to you in your UV, it will happen that not only this segment I lives in UV, but also his parent lives in UV, or maybe the neighbor of its parent lives in UV. Some of those things happen. So if this happens, then this is not the biggest thing which live in UV. So we will have the contradiction. Or no, we say that, okay, if the biggest thing is the segment, then it's big. It is at least 1 divided by 20 of UV. And now we want to say that the first coordinate will distinguish everybody. And why it will distinguish everybody? Because let's look on this picture. Say this is our point U, this is our point V. Somewhere here there was this long segment, and this long segment produced a lot of difference on phi1. So phi1 is at least by this lemma about not by lemma, just by definition of the first coordinate, we have that it is taken from the address, and thus we will have that the first on the segment, the first coordinate is isometry on its ends, and from this, if we go from this segment to the right, if we move the right point to the right, and we stay in our contour set K, then the first coordinate can only increase. So we can transition from, we can say that first coordinate changes a bunch when we go from this point to this point, where this point is the rightest point of the hole in which U lies, and this point is the leftist point of the hole in which V lies. Maybe I should use this picture. No. And finally, we have to say that on those intervals, we will not mess up our first coordinate too much, but those intervals, they are smaller. Our segment was the biggest thing, so they are smaller. And how first coordinate changes when we go to the hole, it doesn't change much because we can apply this. So when we sit in the hole, our first coordinate is, so we can apply this and say that in the holes the first coordinate will not change much. It is weird to apply this because here it says do not apply to the first coordinate, but we apply it when we consider our curve when we consider a curve which has its domain to be with the domain H, and that means that its first coordinate is not our original first coordinate. It is the coordinate which corresponds to the color of H. So we can use this and obtain that the first coordinate will distinguish these points U and V. And the second, okay, I ran out of time, but the only interesting case, so there is everywhere this argument about why something is, if we took something biggest, then it's big in comparison to UV, and then you have to apply either this lemma or the lemma which or this part and get the upper bound. So you say that your coordinates that you want to study change a bunch on this big thing, on the biggest thing, and you bound from above all the rest using one of those statements. So it's pretty much all the same here. So I can finish here, I guess. Or somebody wants to hear it a lot. Or somebody has questions.
Last question.
Okay.
What can you say about Hausdorff dimension of your curves which you embed in Euclidean space?
Hausdorff measure?
Hausdorff dimension.
Oh, Hausdorff dimension. I guess
Yeah.
Hausdorff dimension is less or equal to the dimension of the target space.
Okay, yeah. But under some condition, it can be as you like.
Do you mean that maybe exist some holes which have very large Hausdorff dimension?
No, I mean,
or some curves which have very large Hausdorff dimension?
yeah.
Yeah, I think if you take like a snowflake curve with a so you take helix just 0, 1, and I can't move. So this guy with epsilon equals to 0.0.1, then it will have a high Hausdorff dimension. That's my feeling. Not sure what is the proof, but I was suspect this guy to be of a high Hausdorff dimension. Okay, maybe any other questions?
Well, if there is no other questions, I would like to thank you and say that next time our speaker is Sasha Smirnov.
Nice.
Okay.
So yeah, let's finish.
So, вы умеете отключаться?
Yeah, probably. I can just close. Okay, I can stop share.
No. You should finish the meeting.
Okay.
Или сделайте меня этим самым хостом.
Okay. Yes. Я справился, кажется.
Не,
У меня пишет, что вы хост.
пока я разговариваю, и вы меня слышите, значит, не справились.
Не, я справился с тем, что сделать вас хостом.
Что меня хостом сделать? Ну все, тогда, so thank you everybody. So let me finish. My goodness. Okay. Goodbye.